for those of you that are not zooming in, but watching this, and I'll send this data out to you, but this is for the mini lab. Oh, come back here. So that was your maximum height. That was the total time that the ball was in the air. We'll talk about that. But for those three of you that are watching this, that's the data that you need for the last lab. Okay. So let's talk about problem number 4. Okay. So that's where ball went up, ball came down, had a total flight time of 4.40 seconds. So if 4A is wrong, everything is going to be wrong. So your answer to 4A should be around 21 meters per second. Okay? There you go. Because literally, if that's wrong, everything else is going to be a train wreck. And your maximum height should be around 24 meters. So your answer to 4B should be around 24. Kara?
So on 4B, I ended up using the 1/2 parentheses V plus V naught times time.
Yes?
Because when I did the 1/2 AT squared plus B naught T, I got a negative.
No, bad.
Well, I ended up getting the positive number using the first formula, but the second one was
No, because if you use, you should get the same answer no matter what. Okay? So to get your, because the beauty of this one is that this is like a function equation. You can plug in any value of time at all and generate that, how high it is at that point. Okay? And so there's no way you should get a negative value out of this. So let's just make sure, let's figure out what went wrong. Okay? So you've got 1/2 times negative 9.8 meters per second squared. Now what did you use for time?
2.2
Yeah.
seconds.
Now did you square that?
I think I did, yeah.
And then plus 21.6 meters per second times 2.2 seconds.
Maybe I forgot something. I ended up doing the other formula and I got.
Yeah, either one will work, but I just want you to understand that if you do this, you should be getting that same answer. Okay? All right. So, there's that. When you get to questions number 5 and 6, 5 and 6, I'm going to tell you right now, 5 and 6 has nothing to do with going backwards, okay? So I don't want you to say, oh yes, it was going backwards or something like that. I don't want you to associate negative velocity or negative acceleration with going in reverse, okay? So your answers to, I'm going to tell you right now, 5 and 6 have nothing to do with going backwards, okay? Nothing to do with it. Now, on number 8, here's what you should have for your velocity time graph on number 8. So, you're going to have something like this, okay? So, one's going to start up here at 450, and the other one's going to start up here at 600, and that's going to be at 43 seconds. So, on number 8, when you draw the velocity time graph, so here's the setup. You have one spaceship traveling at 450. You have another one that looks like a test tube traveling at 600. They're both at the same spot at the same time. So 43 seconds later, because the total time is 86, so 43 seconds later they're going to stop, and then they're going to come back and end up back at the same point. So one's going to go from 450 to 0 to negative 450. The other one's going to go from 600 to 0 to negative 600 in the same amount of time. So clearly, what you should see is the one that undergoes the bigger change in the velocity in the same amount of time is going to have a bigger acceleration because it has to go from 600 to 0 in 43 seconds. This one just has to go from 450 to 0 in 43 seconds. So, on number 8, both of your accelerations should be between like negative 10 and negative 15. Okay? So that's kind of your range on your accelerations on number 8. Both of them should be between -10 and -15. And all you're finding, basically, if you think about it, all you're finding is the slope of this line. Oh, here's 0, 450, here's 43, 0. Here's 0, 600, 43 and 0. So all you're doing is finding the slope of the line. Now, let's talk about number 9, because I promise you, you're going to have a problem like number 9 on the test tomorrow. Okay? So let's make sure everybody understands number 9. I promise you there's going to be one like number 9. So, here's the rocket, okay? And it has an initial velocity of 0. Now, here's what's a little bit different about this problem. Up to this point, like when I threw something up in the air, we looked at it from as soon as it left your hand, okay? If we pushed the cart, it was as soon as it left your hand. With rockets, because we're starting at 0 and it takes such a long time to get up to speed, we worry about that part. Because if I just throw this thing up in the air, oh, okay, well, the focus is what happens after it leaves my hand. With a rocket, you have to focus on, well, what is it going to do to get to that speed? So, your initial velocity is 0. You're told that it's going 30 meters per second when it's at a height of, so there's my final velocity, and then it's going to be at a height of 25 meters. So you want to calculate that acceleration. So you're going to use that equation because you don't know time. And you're going to go, okay, v squared minus v naught squared over 2d equals your acceleration. Okay? So what's going to happen here is that, you know, the final velocity is 30 meters per second. You know, your initial velocity is 0, and you know it goes up to a height of 25 meters, which is about 10 times the height of this ceiling. So this thing isn't like in orbit, okay? Right? Anything like that. So this is going to get you your acceleration. So that acceleration should be very, very close to your age right now. Okay? So your acceleration should be around 18. Okay? That's what that acceleration should be. So, now, here's the deal. You want to figure out the time. There's a couple of ways you can figure out the time. What I would recommend is that you go v equals v naught plus at. You know your final velocity, now you know your acceleration, and you know the initial velocity. So you know everything now except for time. So your time on number 9, that time should be between 1 and 2 seconds. Okay, it isn't very long. Okay, we're not going to fire this engine for too long. It's like, bam, fire the engine, whoop, takes off. We're going to shut off the engine. Kara?
So it's speeding up, right? Because we're not counting like the other labs. When we go up, like usually we say they're slowing down.
Yeah, so what's happening, so this is like analogous to me throwing this thing up in the air. So what we're looking at is what's happening while this remote control is in contact with my hand. Okay? So it's like, here's the rocket. Okay? And when I'm throwing it, that's like what's happening now. This is when that rocket engine is being fired. Okay? Now, as soon as it leaves my hand, and I stop the force from the rocket engine, what's the only force left acting on it?
Gravity.
Gravity.
Okay.
So initially, what's happening is that once you fire the engines, you're going to have a small velocity pointing upward, and then that's going to get bigger. Okay, that's the whole point of the rocket engine, right? So initially, I'm going to have a positive velocity and positive acceleration. That's what's making the rocket engine speed up. Okay? Good with that. Okay? So then you're going to use this to find your time. So your time should be between 1 and 2 seconds. Okay? So we're not going to fire this engine for very long. So what's going to happen on your velocity time graph, okay? You're going to start at 0. You're up to, 30 meters per second. and this is going to take about 1.5 seconds, okay? Now, make sure that I tell you that you're going to keep a running clock. So at the end of 1.5 seconds, you imagine you have a stopwatch. So at the end of about 1.5 seconds, this thing is going 30 meters per second. So that would be like me taking this thing, and it's going to be in contact with my hand for about 1.5 seconds. Then I'm going to let go of it. So this goes to this whole idea of Jedi Stoffelwall. Stop the force and watch. So once I shut off the force from the engines, what's the only force left acting on it? Gravity. And what's the acceleration caused by gravity?
-9.0.
Yeah. So on that next question, at that point you shut off the engines, what's the acceleration? Don't make it difficult. The acceleration is just going to be negative 9.8 meters per second squared, because the only force acting on it is gravity. So at that point, I had some positive acceleration of about 18 meters per second squared, okay? That's my acceleration. Now, and this is going to play out on the test as well. And so I'm going to tell you, keep a running clock, and then write down the value of the slope of the line in each segment. So this is what I want to see. Oh, here's my slope. That's 18 meters per second squared. There you go. Now, at that point, I shut off the rocket engine. So that's like me throwing this thing up in the air. Kara just said the acceleration due to gravity is negative 9.8 meters per second squared. So at this point, this graph is going to start to slope down like this. Okay? So you're going 30 meters per second, and you're going to go to 0. Now, it's like this. You have $30, okay? And you have to spend $10 per second, okay? That's how much your bank account is going to drop, $10 per second. Well, you're going to go from 30 to 20 to 10 to 0. So just as a rough estimate, my time is going to be about 3 seconds for it to go from, so I went from 0 to 30 with an acceleration of 18 meters per second squared. So then my acceleration becomes negative 9.8 meters per second squared. We got to figure, oh, that's going to take longer to go from 30 to 0 because my acceleration isn't as much. Okay? So when you get, so you're going to find this time here, oh, come back here, which is going to be about 3 seconds. So when you draw this out, when you draw your velocity time graph, you're going to take that initial time, which is going to be about 1.5 seconds, and then you're going to add another 3 seconds to it. So you're going to end up out here at about 4.5 seconds. Okay? Here's what you don't do. Don't find that second time, which is about 3 seconds, and go to say, okay, oh, this is 3 seconds. That's when it's going to be at its maximum height. It's not. The engine is going to fire for 1.5 seconds. Then it's going to take an additional 3 seconds for it to reach its maximum height. So this is when you shut off the engines, okay? This is when it reaches its maximum height. And I promise you, you're going to have a problem like this on the test. It's going to be the second to the last problem. Okay, I'll even tell you where it's going to be on the test. Second to the last problem. It's going to be just like this. The only thing I want to do is change the numbers. Okay? Got it? Any questions on this? Everybody cool? Now, as soon as I shut off the engines, what's going to happen to my velocity vectors? It's just like me throwing this up in the air. As soon as it leaves my hand, what happens to those velocity vectors? What do they start to do?
They get smaller.
They get smaller. They're still pointing up, but they're getting smaller. Okay? So now I'm going to have negative acceleration. So when the engines are fired, my velocity vectors are getting bigger. I have a positive velocity, positive acceleration. Once I shut off the engines, then they're going to get my velocity. Oh, screwed that up. I drew them the wrong way. So once I shut off the engines, then they're going to get smaller, and now I'm going to have negative acceleration. Okay? Cool with that. All right, so if you look on that mini lab, kind of using your data, So you guys had a total flight time of 1.25 seconds and a maximum height of 2.18. So here's what I want you to realize, is that your velocity time graph is going to look something like this, okay? It's going to be a straight sloping line. Your position time graph is going to look something like this, okay? And that maximum height on your position time graph is going to be 2.18 meters. Its maximum height is going to occur halfway through this time, okay? Halfway through the time is when your velocity time graph crosses through zero, because that's when it's going to change direction. So take 1.25, divide that by time. That's when this goes to zero, that's when this goes to zero. So, the 2.18 meters, this is what I would do. Okay, if you gave me this problem, this is what I would do. I like triangles. I sit here and go, oh, this is this area of this triangle. That's 2.18 meters. I know my area of the triangle. I know my base is half the time. What I don't know is the height, which is my initial velocity. So this is the exact same concept that you used on the very first lab that we did, where we pushed the cart up the inclined plane, okay? So one of the things you've got to be able to do is use the resources that you have. It's like, oh, we did something like this in a previous lab. Go, if you don't remember how to do it, go back and look at what you did in the lab. And this is why you write stuff down, okay? This is why you show your work, so that when you have to go back and try and reconstruct what you've done, now you look at that and go, oh, that's why I did that. Yeah. Now, if you want to hold on to this assignment and hand it in tomorrow, if you want to use it as kind of like part of your study guide, you can. If you're done with it and you're feeling good about it, you can go ahead and hand it in, okay? It's whatever works for you, all right? Anything else you want, anything at all, if you have any questions at all, if your answer is right or wrong, this is the time to ask. Kara?
So on 9, the second part of 9, so on the way up, it's speeding up, and on the way down, it's actually slowing down? Is that what you were saying?
No, no, no. Okay, we're not talking about falling down, okay?
It's when the engine shuts off,
Yeah, so when I shut off the engine, it's still going up,
but it's slowing down.
but it's slowing down.
Okay.
So that's like me when I throw this thing up in the air. It's going up, but it's slowing down.
Okay.
When it's in contact with my hand,
It's speeding up.
it's speeding up and it's going up. Because the force that I'm providing by my hand is bigger than what's gravity trying to pull it down. But as soon as it leaves my hand, gravity says, ooh, you're all mine, and I'm going to make you slow down. So yeah, so it's speeding up and going up, but then it's going up and then slowing down. So don't confuse on this one. This is not maximum height. This is not a position time graph. This is a velocity time graph. So maximum height is going to occur here. This is when you're going to shut off the engines. Because if you think about F equals ma, well, the only way that you can change the slope of a velocity time graph is to change the acceleration. The only way you can change the acceleration is if you change the force. So when I shut off the engines, the only force left acting on it is gravity. That's creating that acceleration. Shivani?
If it was a position time graph and it had like the jets on it or whatever at the beginning,
Yeah.
would it go super fast and then
Yeah,
first
so
and then
you're-
not go at the same time?
Yeah, so your position time graph, okay, it would start like this, right? And then it would be going faster and faster and faster. So, and that's why these lines are becoming more and more steep, okay? So then at this point, at about 1.5 seconds, I would shut off the engines. So then the graph would do this. And then, because once I shut off the engines, then it's still going up, but then it would be slowing down. Then, when it reaches its maximum height, then the graph would go something like that. So if you could draw a position time graph, it would look like this. It would start off slow, speed up, boom, I shut off the engines. It's going to start slowing down, and then it's going to fall all the way back down to the earth. So that's what the position time graph would look like. I won't ask you to draw anything like that on the test, but that's what it would look like. It's a good question. Okay, Anything else? Speak now or forever hold your grade. Okay. Make sure your graphs are numbered and the axes are labeled so I know what they are. Okay? Just don't randomly put graphs on there and think I'm going to know what they are. I'm not. Okay? Make sure that you label everything. Okay, so here's what's going to happen next. So this is like this big kind of summative problem. So I'm going to give you this problem, then I'm going to give you about 10 minutes to try and work it. So what's going to happen on this problem, and I'll give you all this information on this sheet of paper. You who are watching, I'll send this information out. So you've got a building, and the building is 8 meters tall. Okay? And we're going to make the ground the reference point, so that's 0. So imagine that you're standing on top of this building, and I'm going to throw a ball up in the air, and then it's going to fall all the way down to the ground. Okay? So, I've lost my golf ball. Okay. So, imagine this, like, I'm stopping, so here's like the top of the building, so I'm going to throw the ball up, and then it's going to fall all the way down to the ground. So you're here, doink, like this. So, there's a whole bunch of things that you want to find, like the time up, the maximum height, the time down, the velocity of impact, and then the total amount of time. So I'm going to give you this sheet of paper, and I'm going to give you some time to work on it. So what I want you guys to do is that when you guys think you have part of this work, and here's the other thing you'll see with this problem, there's probably literally a dozen different ways that you can work this problem depending upon how you approach it. So, just because you work it one way and somebody works it another way, as long as you get the same answer, it doesn't matter, okay? Because literally there's a bunch of different ways that you can work this problem. So, when you get it done, so here's what I want you to do. And so we'll do a little comparison. So like, let's say Matt thinks he's figured out what the maximum height is going to be. So here's what I want. I want 3 things. I want you to come up and I want you to write the solved equation, okay? I don't want to see what equation you started with and then solve it. I just want the solved equation. So he's going to say, oh, distance equals whatever. However, he's going to find that maximum height. And then I want the numbers and then I want the answer. And make sure that you put the units with it, okay? So I want to say, hey, D equals, here's my equation. D equals, boom, here's the numbers, boom, there's my answer. 3 things. So I want maximum height, and then you're going to have, let me put all this, your, time up, your time down, your velocity at impact, and then time total. So, when you think you know how to work it, come up here and say, here's how I'm going to get my maximum height, here's my time up, here's my time down, velocity of impact, and the total time is easy, that's just the sum of those 2 times. So, visualize this. You got to find out how long it takes to go up to here when the velocity is 0. Now, here's the whole, let me give you another hint. When this thing starts to fall, look, you can view it as like a separate problem. Because when it starts to fall, Carol, what's the initial velocity?
0.
Yeah, so you're going to go from 12 to 0, and then if you can figure out how high it is, then it becomes like a completely separate problem. Oh, this ball is this high, it's going to fall this distance, how long is that going to take? Okay? And then you can figure out how fast it's going when it lands. Like I said, there's probably a dozen different permutations on how you can work this problem. There isn't a set right way, okay? It varies depending upon your preference. So, I'm going to hand out this little paper, I'm going to stop that camera, I'm going to give you all about maybe like 10 minutes. Once you think you've got one of these worked out, and no, I don't want one person working all of these, okay? So there's 4 of you. I have 4 kind of big things that I want: max height, time up, time down, and velocity to impact, okay? Now, the other thing that you'll see is that you have to start to use values that you found to get like the time down and the velocity to impact, okay? You have to use numbers that you have already found. So you're going to have to take the leap of faith and use numbers that you already found. Okay, so here we go, kids. All right, kids. So let's talk about what we have. So let's talk about that time up. Okay, let's just start with this concept. Now, so your velocity time graph, we haven't talked about that. Let's jump down to the velocity time graph. So your velocity time graph is going to start at 12 meters per second, right? Now, how do you know your time up is going to be more than 1 second?
Because, isn't the maximum height at like 3 seconds? No, wait, that was the rocket ship.
Huh?
Never mind.
The maximum height is greater than 12 meters, so it could be.
Not the maximum height.
The acceleration is only negative 9.8 meters.
Oh.
Yes.
It's less than
Your
12.
acceleration is negative 9.8 meters per second squared, right? So if my initial velocity had been exactly 9.8, it would take exactly 1 second to go to 0, right? But since my velocity is bigger than 9.8, it's going to take more than 1 second to go to 0. Okay? So don't be afraid to look at an answer and go, oh, does this seem reasonable? So your velocity time graph is going to do something like this, right? You're going to start at 12 meters per second. You're going to go to 0. And remember, this is when you're at your maximum height, is when your velocity time graph crosses 0. So, if you look at what Elise did, this is perfect. This is what I want to see. Here's the solved equation. Here are the numbers with all the units. I get 1.22 seconds. Now, she started to divide that by 2, okay? Don't divide that by 2. That is how long it takes to go from 0 to 12. Okay, that's it, right? So don't divide by 2. That is how much time it takes. So at this point, we know that we're at 1.22 seconds. Now, if you wanted to, on your velocity time graph, you could find the area of this triangle. You could take 12 times 1.22, take half of that, find that area, that's your maximum height, and then add that to 8 meters. You can do it that way. But the only problem is if this time is wrong, then your next calculation is going to be wrong. Okay? Now, if you look at this, so it's a little bit jumbled, okay, but we got there, okay, so we're good, okay. So I got v squared minus v naught squared over 2a. I took that equation and I solved it for distance. So this is why you just can't drop this out, okay. You have to have, and here's the reason why. My maximum height has to be a positive number. Because if you just put in 12 squared divided by 2 times negative 9.8, you would get a negative maximum height, which doesn't make any sense. That's why you have to have this 0 minus this quantity squared, and you have to have that negative 9.8. Okay? You have to work this problem consistently. So she got 7.35, added it to 15.35, boom, there's my maximum height. Okay? So at this point in the problem, here's this building. This ball is starting to fall from 15.35 meters above the ground. Okay? Now, here's what's going to be important. Kara, when it starts to fall, what's my initial velocity?
0.
So on the way down, it's like this is a completely separate problem. It's just like I'm holding a golf ball 15.35 meters tall, and I'm going to drop it. Okay? How it got to that point doesn't matter. Whether it's falling down from a maximum height or if I just hold it. On the way down, okay, on the way down, oh, my initial velocity is 0. So V naught's going to equal 0. Now, if you look at what Matt did, okay, he's got the right idea, but we need to tweak some things. Because part of your grade on this problem on the test, and this problem is going to be the last problem on the test, it's going to be worth 15 points, which is more points than any other problem on the test, okay? So you have to make sure you know how to do this. And part of your grade is going to be, can I track what you have done? Now, Matt started off kind of on the wrong foot because he had V naught squared minus 2AD. He's trying to find the final velocity, right? So this should be V naught squared plus 2AD. Now, here's where, if he had added it, Matt has one thing right in here, but he has one thing wrong. If you actually add this, and the way Matt has this written, he would have a negative underneath the radical, which would lead to imaginary velocity. Okay? That's a train wreck. But here's the deal. This displacement on the way down is actually a negative value. Okay? Because of the fact that starting at 15.35, my final position is 0. So if I take 0 minus 15.35, that makes that a negative displacement, and that should be meters. So if I come in here, I want to tweak this a little bit, Matt. I'm going to make that negative 15.35 meters. Then, he's still going to get the same answer. And this is what Matt did right. He chose the negative root because it had to be going down. Yes?
So when you're doing that, and when the square root, if it's negative, but you have to change it, we know the velocity is going to be negative, right?
Hold on, what do you mean by it, when you say you
So-
change it?
So 15.35,
Yeah?
that's positive, but you would change that to a negative, so it won't be an error.
Yeah?
So that means the velocity, even though it will show up as positive, because we changed it
You just have to
negative.
choose the negative root.
So
Yeah,
we
but
know-
that's why when you look at it in the context of the problem, you go, okay, well, that ball is going to be going down when it lands, and I've defined down as being negative, so yeah, you just choose the negative root.
Okay.
Okay?
I think the velocity is actually,
Huh?
I think the velocity is actually positive negative 17.34 I meters per second.
Okay. let's-
Oh, I got negative 12.26.
No, there's no way.
What did you say you got, Shawna?
Negative 12.26.
Nope.
I think you did times 8 instead of, because that's what I got the first time. Or I think I got around that the first time. Instead of 15.35.
Oh.
Now, that's one way to find the velocity at impact, what Matt did. Is there another way that you can find the velocity at impact?
Well, you have to know the time, right? for-
Yeah, now, let's talk about the time down. Because the other way you can do it is you have to have the time down. The only way that you can find the time, this is what I would recommend for the time down, because this is the simplest thing. What I would do for the time down, I'd go, oh, distance equals 1/2 AT squared plus V naught time. On the way down, what's your initial velocity? 0, right? Okay, so that part goes away, because I'm dropping it from 15.35 meters tall. So if you solve for time, and this is what's critical, you get time equals the square root of 2D over A. So I multiply by 2, I divide by A, I take the square root of that. This is a wonderful, wonderful way to find time down when you know how high something is, okay? Embrace this idea. It saves you a lot of heartache, okay? Now, here's what you have to watch though. This has to be 2 times, and this is what I'm going to look for. You've got to put that negative 15.35 meters underneath that radical, and then divide by negative 9.8 meters per second squared. Okay? So, and so help me, on the test, if you put positive 15.35 divided by negative 9.8, I'm going to write, wow, imaginary time. Kind of cool. Okay? Now, somebody run these numbers. Take 2 times 15.35, divide that by 9.8, and then take the square root of that.
One point seven eight, 7.
1.77 seconds. So hopefully that makes sense. It took 1.22 seconds to go up. Okay, so from here, it took 1.22 seconds to go up. But it's going to fall farther, so it's going to take longer to fall than it is on the way up. Okay, does that make sense? So my total time is going to be 2.99 seconds, so about 3 seconds. Now, here's how you can use that time down of 1.77 seconds. Here's another way to find the velocity at impact. So that velocity at impact, you could go, okay, well I know V equals V naught plus AT. On the way down, like Kara said, my initial velocity is 0. Okay? I know my acceleration is negative 9.8 meters per second squared. I know my time is 1.77 seconds. So, Matt, take 1.77 times negative 9.8.
Negative 17.34.
So, negative 17.3 meters per seconds. So, the advantage of this one is that it automatically generates that negative sign on the velocity. Okay? That's the advantage of it. Now, here's what you have to be careful of, and this is what you have to think through. If you're going to do this to get the velocity of impact, basically look at your graph and you're going, oh, I'm starting here at 0. Okay? It's basically like a new graph. You're starting here at 0. It's going to take you 1.77 seconds. Then I'm going to find the velocity here. Okay? Now, if you want to use 12 meters per second as your V naught, then you'd have to use the entire time of 2.77 seconds. Okay? So I don't care which one you do. Hello.
Hi.
She's a full-time remote student, so she's not in school at all.
Okay, thank you.
I figured out what I did wrong.
Okay.
I didn't multiply it by 2. So instead of plus 280, I just did plus 80.
That will happen. Okay, so that's why I said there's a bunch of different ways that you can work this problem. I don't care how you work the problem. Now, like I said, here's going to be your last 2 problems on the test. The second to the last problem is going to be a rocket problem. The last problem is going to be a problem like this, where you're on top of the building, you throw the ball up in the air. There's a problem like this on the review. Okay, it's on the second page. There's a problem like this on the review. You have to get good at working this. Literally, it's just like you're learning how to play soccer or whatever. You're not going to kick the ball one time and go, okay, I've got it. Okay, it becomes repetition. If I were you all, you know this is the last problem on the test. I'd work this problem, I'd take this problem, I'd work it again from scratch. There's a problem like this on the review. Work that problem, and then look at the answer key to see that you got it right. Then change the numbers. Oh, I'm going to make the building taller. What's that going to do? Oh, I'm going to throw it at a higher velocity. Oh, what's that going to do? So, it'll be the biggest test that you've had. There's going to be the first page, probably the first couple pages are going to be all multiple choice questions. Then you're going to have some problems to work out. Okay? Now remember, if I ask you, if I said, hey, you know, I'm going to throw something up in the air, and then what would be the slope of the position time graph at a particular point in time? Remember the magic code. If I say, what's the slope of the position time graph, what am I asking you for?
Instantaneous velocity.
The instantaneous velocity. Okay, so remember that. The slope of your position time graph gives you your instantaneous velocity. So that's going to be like the magic code. Okay? All right, I am done. So what you have, what I'm going to hand out is that you're going to get 3 pieces of paper. One is all the topics that you need to know for the test. The other one is a blank set of problems for and then the other one is all of the problems worked out, okay? So, again, this is what I would do if I were you all. I would take that blank review and I would treat it just like the test. It's like, okay, I'm just gonna work this I'm just gonna work this straight from the beginning. Remember, you're gonna have your equation sheet. So I would work it, and then I'd go back and see how you did, okay? And basically use that answer key to check it. Because what happens if you look at what I did first, you can go, oh yeah, that's how I would have solved that problem, okay? Let me give you a hint. I'm not gonna give you the answer key to the test tomorrow. I know, I'm just not that nice. Okay, so I'm gonna hand all that out, I'm done. You're on your own.